the mechanics of muscle contraction, which we began last week, and then begin anatomy. Have muscle anatomy for today and Thursday, and we'll have one more week after this week. It'll be on introduction to hash potentials, theoretic potentials, and so forth, and that'll be next week. So we have still 2 weeks, 4 weeks before the next exam. Okay, I had the first unit 1 exam review right before class today. If you'd like to come, and you certainly don't have to if you think it's useful. The next one will be right after lecture today, focus for students for the last name G through M, and it'll be in the room right behind this one, ES 124. Should be LA. Yeah, it should be LA, shouldn't it? Well, anyway, I think it's in, that's interesting. Maybe it is over there in the ES building. I didn't even think about it. I bet it is. That's the number she gave me. So it's over there in the Education Science building next door. For some reason, I was focused on 124 behind us. And anyway, the iClicker questions will be today at the end of lecture. So let me go ahead and get started. Thought I'd review just a little bit before we get into the lecture from last time, because it's some pretty important material, and I kind of sped through it like I usually do with the last lecture. So just to remind you, an isotonic is the mechanical characteristic of muscle where you study muscle where it's called same tone, where the muscle lifts a weight and is able to shorten. And so that's isotonic contractile activity, and you can see it exemplified here. The muscle has a given weight on it, you stimulate it, and it shortens. And in that type of contraction, we measure or study the experimental study the contraction by measuring the displacement or how far the muscle moves with time, and that's represented by the graph on the bottom. Isometric is the mechanical model in which the muscle is fixed in position between two fixed objects, and you stimulate to contract. So it doesn't really shorten, although the muscle fiber contracts and increases tension. So here you measure force. The transducer down here measures how much force change there is per time. And as I said last time, we have both types of contractile activity in all our muscles for different purposes, and we'll see some examples of that all the way through the year. I also defined the term motor unit last time, and that's all the individual muscle cells or fibers that are innervated by a single motor neuron. So motor neurons often come out and then branch or form collaterals, and these branches go to different cells. Each individual muscle cell has only one neuromuscular junction. It only meets one nerve, but a given motor neuron may meet hundreds of and innervate hundreds of fibers, and that cluster is called a motor unit. So a motor unit, group of muscle fibers innervated by a single neuron. And some of these are hundreds to thousands of cells in size, and some of them are quite small. So we always add the little corollary that the larger the motor unit size, the greater the force. So if you have a motor unit that supplies hundreds of cells, it'll be able to produce a tremendous amount of force. Where the opposite is true in our very dexterous and fine controlled muscles, where a very small motor unit, often just a couple of cells in size, is controlled by single nerve. So this would be, as we said last time, something like an eye muscle or something like that. Okay, then I put on here a little bit about a muscle twitch, and we'll get back to this story subsequently, but a muscle twitch is the contraction that occurs when we give a single stimuli to a muscle. And so right here would be the stimulus, and there's always a period of time where nothing occurs before the muscle starts shortening. And we went through those events when we talked about all the series of cascade of events that occurs between stimulation of the sarcolemma and actual ratcheting of the actin and myosin filaments. So those are the events of EC coupling, and they occur during the latent period. The period of contractions when more and more force is being produced, and then the period of relaxation goes back to the resting period when the muscle is now regaining its length or not lifting as much weight, so forth. So it's called period of relaxation. And this duration of the single twitch varies tremendously between different types of muscles, be them skeletal or smooth and so forth. And we'll talk about this when we get to the other family of muscles. As I said when I started this discussion, we always present, first of all, skeletal muscle activity and then broaden it into cardiac and smooth. And so this is the story right now for skeletal muscle. When we do the other types of contraction, we'll go more into duration and why it's different. So now we're going to move into the control of force. How do we determine how much force a muscle can lift or produce? And one way to do it is what we call spatial summation. And this is really the explanation for the phenomenon called spatial summation. You can stimulate a nerve going to a muscle with a very small amplitude and not get any force at all. So we call that a subthreshold stimulation, meaning it's below the amplitude, below the voltage that's required for that muscle to present a measurable force. So that would be a subthreshold stimulation. As you increase the amplitude of stimulation, you get an increasing amount of force produced in the muscle, and that's primarily because as you stimulate that nerve with more and more amplitude, more and more voltage, you're going to activate more and more of the axons in that nerve, and each of those goes to its motor unit. So you're bringing in more and more motor units up until number 7 in this depiction, when every axon in that nerve is now activated, and then you have what's called maximal voltage. Supermaximal is just the term which we sometimes use, which means that the voltage is above maximal. In other words, maximal is the amount of voltage that will that'll activate every cell in that muscle. Any amplitude above that is called supermaximal because it's not effective in activating any more cells. This whole phenomena is called spatial or motor unit summation, which means we're bringing in more and more cells in a given muscle and creating more force. So you're increasing, a good way of saying it is you're increasing the fraction of active motor neurons and therefore motor units. There's another type of regulation of force called frequency summation, and that's shown here. So here we have a single muscle cell. You could use a given muscle or even a single muscle cell and stimulate it with at 5 hertz, which means 5 times per second. And so here's one stimulation, and here's another where the red arrows are, and each time you get a separated twitch. If you increase the frequency, let's in this case double it, so you're giving twice as many stimulations, or 10 hertz per, or 10 stimulations per second, you'll start seeing that before the twitch can relax, you're adding another stimulation, so the force is actually summated, so you're getting more and more force. And this phenomenon is called treppy, because the Germans called it treppy because it looks like a staircase. So before the muscle can relax all the way, you stimulate it again and stimulate it again, so it looks sort of like a staircase phenomenon. If you stimulate it even further, this is 25 hertz, you'll start getting a much higher force than you do with a single twitch, and almost fusion of the muscles into a rigor state. And that, when it does reach fusion, we call that tetany. So tetanus is when you have all the cells of a given muscle, or not necessarily, all the cells at that motor unit are maintained in contracture, and so it looks like a fusion of force. And it's often you get 3 times more force in tetany than you do in a single twitch, 3 to 5 times more force. The mechanism for the increased force that occurs in tetany has gone through some evolution, and now is believed to be by two different mechanisms. So I'll explain both. I actually think myself the contribution depends on the type of muscle, but in many muscles, the second mechanism, or I explain, is more important than the first. However, the first is more easy to understand, and that is if you start stimulating the muscle faster, then the sarcoplasmic reticulum can trap the calcium. You have a higher average calcium in the interstitial or the sarcoplasmic fluid. So you stimulate it, calcium's released, you stimulate it again, calcium's released, and so the mean concentration of calcium starts going up. And as calcium concentration goes up, you end up having calcium bind to even more troponin and release more inhibition and get more and more force. That this phenomena is debatable, and I know in some muscles you bind up all the troponin with even a single twitch. So this is arguable, but I think there are some muscles where this does occur, and it's definitely true in other classes of muscle besides skeletal, but it's certainly not the whole story. So it's not just that when you stimulate faster and faster, you elevate the intracellular calcium, you get more force, because we can prove in many cases that all the troponin is coupled to calcium, all troponin C, with very, very low, and the additional calcium is not having any effect. So this is part of the story, but just as important is a second mechanism that's responsible for this temporal summation. And it's a lot harder to understand. It's called consumption of series elasticity. This also gives me an opportunity to describe what we call series elasticity and the mechanical characteristics of muscle. So muscles are far more than just actin and myosin proteins that interact. They also have passive elements, we call them, that exhibit elasticity. All biological tissues have some elasticity. And so what happens mechanically is a sum of both the active elements, sometimes called contractile elements, and the elastic components. And so you have to take all these into account when you're trying to explain what's going on when the muscle contracts. And we often draw little sketches that look something like this. So, and this is a mechanical analog. It's not strictly meant that you can apply parts of a muscle exactly to either analog, either model, but it works mechanically and definitely is proven to be somewhat close to what happens in a muscle. So contractile elements are the parts that actually are responsible for creating force or decrease the width of a sarcomere. And the series elastic element is tissues that are in series with that stretch. You can think of it as having an exact analog anatomically if it helps you to understand it. And that is, you can think of the contractile element as the actin and myosin filaments that are coming together. And you can think of the series elastic element as tendons that have elasticity. So when the muscle shortens, that stretches the tendon. However, it's far more complex than this. We know that even signal cells have series elasticity that you don't even have any tendons attached to. So the series elasticity is a component of Z lines, people say, of the actual cross bridges themselves and many other things. But essentially the take-home story is that muscles act as though they have something that increases their force, which is a contractile element as you stimulate it, and another series or group of elements that can be stretched much like a spring and eventually impose that force. Well, what does this real complex story have to do with what we're talking about? This is a graph which you couldn't ever reproduce exactly, but you can kind of imagine that this is what's going on in a muscle cell. So VM, and we haven't talked about membrane potential, but that's what we're talking about next week, is the voltage across that membrane. It's a spike voltage, which you call an action potential. So when the neuromuscular junction releases its neurotransmitter, we'll talk about this next week, it causes an action potential that goes down the sarcolemma and down T tubules. I talked about it a little bit last time. So VM represents the stimulus, if you want to think of it. That's the easiest way. It's the change in voltage that occurs with stimulus. And immediately after that happens, the L channel, we talked about last time, the DHP channel opens, and probably mechanically that forces open the ryanodine channel, and calcium floods the sarcoplasm. So here's the calcium going up, calcium inside the cell. So action potential, then increase in calcium. And the calcium, as we said before, binds to troponin C, and then the tropomyosin moves away from the binding site, et cetera, and so force increases. And so after, somewhat delayed after the calcium spike occurs, the force goes up. So this could be modeled as what happens with a single twitch. And if you're looking at that mechanical analog, you stimulate, the calcium goes up, and so you start having the actin and myosin filaments come in, and the sarcomere width decreases. And initially what will happen is you're going to stretch the spring, but then that spring will eventually, pull on the tendon, and you'll have an increase in force. But the idea here is the spring is going to delay in some amount of time the imposition of force on the muscle. So it's an elastic element that mutes the force as well as delays the force, if you will. And the better way of seeing what I'm trying to do is look what happens if you sustain the depolarization. So this is a single twitch. What would happen if you stimulated the muscle tetanically, if you kept stimulating the muscle over and over again? And that's represented right here. So this would be increasing the hertz, or the frequency of stimulation, VM, and now the calcium will go up, but it stays up. You're releasing it at the same rate that the SR can trap it, so the calcium goes up, and the force goes up and stays up. So what that represents as far as the mechanical model is a contractile element holds its short width, if you will, and then the spring stretches out until, or gradually reaches the force, the full force that the muscle can produce. And so the difference between the force produced with a single twitch and produced with a tetanic stimulation is a time delay, if you will. In other words, let me go back here. So here, by the time the contractile element has started producing its maximum force, it's already coming back to its resting stage. In other words, the calcium's all being trapped, and the actin and myosin filaments are now relaxing and moving back to their resting configuration, and that's about when the force is being produced. So that's why you only get 1/3 the force. You don't hold this contractile element to its shortest length, if you will, the sarcomere to its shortest length, long enough for that series elastic element to produce the force. So if you hold it, if you hold this contractile element narrow, then you'll finally get the spring, if you will, to express the full force. And if you want to think of it as a tendon or whatever, essentially you've just held the sarcomere's narrow width a long time. And like I said before, a single twitch produces about 1/3 the force of tetany. So you get far more force if you do this out of a muscle than a single twitch. So I always like to relate this to reality, what goes on in our muscles. I gave you this last time, is spatial summation play a role in day-to-day life when we're trying to figure out how much weight we're lifting. As I said last time, it certainly does. Our computer, which we call a brain, figures out how much something's going to weigh and presets how many motor units are activated, and then we use the amount of motor units that we need in order to perform a certain task. A more difficult question is frequency summation important as far as force produced? Do we tetanize muscle in order to get more force out of it? And you might say, no, it would be frozen, but actually we do. A twitch is a useless commodity. It lasts just a few milliseconds. And when we're lifting things, we maintain those muscles in contraction. And actually, it's more complex than that. on each side of the bone, and so you're always kind of balancing forces. And what we do probably rather than tetanize whole muscles is we tetanize motor units. So maybe 10, 20, 30% of the muscle we give very high frequency, and that makes the muscle smoothly contract. So we're pretty sure that frequency summation, maybe not complete tetany, is used all the time when we're trying to utilize our muscles for some purpose. Definitely a twitch is not a valuable commodity as far as muscle activity. Another very important mechanical feature of muscle is called the relationship between muscle length and tension, the length-tension relationship. And this is studied in isometric preparation. It has to be. And so you set the muscle at different initial lengths and stimulate it and see how much force it produces. And we use a little device like this. We'll do this in lab in a week or so. And what we do is we put a muscle between a device that can set its length and a force measurement device, which we call a transducer. And we stimulate it, then we stretch it, then we stimulate it again, we stretch it. And so we find out how much force the muscle produces at varying muscle lengths. And if we start here at relax and we gradually increase the muscle force or muscle length, we'll get more and more force produced. Now, if you're just even imagining how this occurs, you realize that as you stretch the muscle passively, it's going to resist that stretch and produce force. If this was a rubber band, it would do the same thing. So if you pull this up, the transducer is going to show more and more force after a certain amount of effort. So once you start stretching this enough that you get the transducer activated, you get passive force. And this bottom line right here represents the passive force that occurs when you start pulling on that or turning that micrometer. And then you stimulate it at each of these and you get the total force. So the total force here is the sum of the force the muscle actively produces, which is the red line, plus the passive force. So L naught, if you will, is the passive force that, no, I mean not L naught, but that bottom line is the passive force that the muscle produces just because of its elasticity, and then at each of these you'll stimulate it and you get more force up to a point and then less and less. The peak force that a muscle can produce is sometimes called physiological resting length, which is kind of an interesting statement. What that means is most muscles are about that length, or L naught. So that's the position that the muscle exists at rest and supposedly the most force the muscle can produce. And beyond that, you get less force. And the rest of this figure explains very simply. It's not a very complex story at all why this occurs. If you start from L naught right here and you start stretching the muscle beyond that, this represents a given sarcomere. And as you pull a muscle passively to greater and greater lengths, you're going to pull apart the actin and the myosin filaments. So the thick filaments are here in the center, and this little thinner line represents the thin filament. And so as you start separating more and more, you're going to have, initially when you stimulate it, far less cross bridges that are effective. So as you pull a muscle further and further away, you're going to have a less number of cross bridges that can interact and can produce force. And so eventually you'll get here where it's totally separated, which is a sarcomere length of about 3.7 micrometers, and then you won't get any active force. So you have to have cross-bridge overlap in order to get force, and when you have every potential cross-bridge overlap, you get the maximum force. So the question that's left is why, when you decrease length below L naught, do you lose force? And most people believe it's because the actin filaments actually overlap and you start losing force because of loss of active or effective cross bridges. So below L naught, you have overlap of actin and less force. Above it, you just have less cross bridges capable of forming. So it's pretty well shown that this is the mechanism of the length-tension relationship. Every book has a different diagram that shows the same thing. This is another diagram that shows the same idea. So you get more force up till you have every cross bridge potentially made, and then you get zero force once you pass that point, and decreases due to overlap and loss of bridges because of overlap. So what about this? Is this an important mechanical thing? Whether our muscles have the most force at a given length. Guys that you work out with, the weight trainers will often tell their clients that their ideal position, they'll say you put the bar in the ideal position to get the most force and make it a lot of effort out of this story. The truth is that our skeletal muscles don't change much in length to produce the force they do. Take, for example, the biceps. The origin up on the shoulder is fixed, and what you're going to move is the insertion, and it's very close to the hinge. In other words, the muscle doesn't change very much to have a large change in leverage, if you will. And most of our skeletal muscles are like that. They change very, very little in length during their active period or even during the resting period. So most physiologists feel that this length tension is quite unimportant as far as regulating force our muscles produce. However, and we'll make a big deal of this later, it's extremely important in the heart and very, very important in smooth muscle. So the other two categories, this is one of the most important mechanical features of the heart and smooth muscle. For example, in smooth muscle, the bladder, if you start stretching it, it becomes more effective in emptying. So the length tension relationship is extremely important in other muscles, but fairly immaterial as far as skeletal muscle activity. Another mechanical feature of muscle is called the length or the force-velocity relationship, and this is studied in isotonic preparation because the muscle has to shorten. So you measure the velocity of contraction compared to the load. So the heavier the load, you can see it's the inverse relationship. The heavier the load, the lower velocity. And this is a very simple relationship. If you have a pickup truck and you want to see how fast you can go from 0 to 60, you try it, and then you put a couple 100 pounds in the back of the pickup truck. You try it again. You put 500-600 pounds. You try it again. And the heavier load you put in the pickup, the slower it's going to go until you put enough load, and it can't even move. The tires just spin. So anyway, this is just the mechanical thing we're all familiar with. If you try and lift something, it's slower and slower. And so this point up here is called Vmax. That's the maximum velocity the muscle can contract at zero load. Every muscle has a Vmax, which means if it actually has no load on it, this is the maximum velocity it can attain. And the isometric point is the amount of weight or force you're trying to lift, which will make it impossible for the muscle to shorten. So when you get up to 4 kilograms, that muscle can't shorten. So that's called the isometric point. So these two intersects on the X and Y axis actually are pretty important and used often to study muscles. For example, don't look at the red line for a minute, just look at the blue lines. This is the effective initial length on that force-velocity relationship. And so if we have a muscle, we were talking about this a minute ago, at L0, at its most effective length, and you put zero load on it, it'll have a Vmax right here, but its isometric point will occur at a pretty heavy weight because every possible cross bridge is functioning. If you stretch that muscle so you have fewer cross bridges that can form, it won't be able to lift things as well at heavy loads, but with no load, it's just going to be just as effective as a muscle with many cross bridges and onward. So it turns out the Vmax is not affected by initial resting length, but the isometric point is. and I've seen large stories written on this, and it's not that hard, but some people model it like a horse-drawn carriage, where if you have 100 horses pulling a carriage, which is this situation, the carriage can carry more, this one 50 and this one 20. So the more horse bridges, i.e. the more cross bridges, the more load you can carry, but the horses, if there's no load, will still run the same speed if there's no load. So anyway, the point is that the muscle has a basic characteristic V naught or V max, but it has a variable isometric point depending on how many cross bridges it can form. And finally, as far as the red line, it's often referred to as the work a muscle produces, or the power. Terms in physiology are often used the same. And it's a pretty interesting phenomenon. In other words, do we produce the most work at the fastest velocity, or when we lift the heaviest load? You can think of it that way. Well, it turns out that it's a factor of both. In other words, work is mass times distance, if you remember from physics. And so if you're not going to lift anything, if it's a zero load, there's no work. And on the other hand, if you're not moving the object you're trying to move, then there's no work. So if you're just working, and people will argue about that because isotonic exercises definitely seem to require a lot of ATP. But in the classic definition in physics, you don't get any work if you don't move the mass. And so zero work right here in the middle of the scheme would be the greatest work, where you get the greatest velocity at a kind of average type load. Okay, so that's the first part. I'd like to get started with the anatomy, and so that is the other lectures. So let me go to that one. Okay, so yeah. Oh, go on. I could have done it. Yep. I'm always bumping it in my pocket too. That looks like what happened. Hello, hello. No. Oh, maybe the battery ran out. I'll try and stay somewhat close to this, although I don't guarantee it. You know me. Okay, so we divide the muscle lectures into two groups. One is the axial muscle. We talked about the axial skeleton. It's the same idea. And then the appendicular muscles, those that are responsible for moving the appendices. And so we're going to start talking about general terminology about muscles first, and then the axial muscle, and then the next lecture we'll talk about the muscles that move the appendices. Okay, so the first story is the connective tissue membranes that surround muscles. And this is a story that you'll see repeated in nerves and other tissues. The outermost connective tissue sheath of a muscle is called the epimysium, and it's represented right here. So if this is a whole muscle, the outer sheath around that is called the epimysium over here. When we do nerves, you'll see the outermost tissue, connective tissue around the nerve, and they're actually the same type of tissue. It's called epineurium, so the terms you'll see repeated. Perimysium surrounds a cluster of cells. We were eating steak the other night, and my beloved wife was sorting through the steak, trying to find the fascicles and the epimysium and endomysium. That's what you do if you have too many physiologists in the family. But anyway, the perimysium surrounds the fascicle, and the endomysium is around a single cell. So here's a cell. These are the myofibrils coming out of the cell. So endomysium surrounds a single cell or a fiber. Now, not only is there epimysium around the muscle, but often there's layers of connective tissue, which we call a fascia. And you'll probably see that when you're dissecting the cats in lab this week. Tendons are connective tissue dense regular connective tissue we talked about before that bind the muscle to the bones. So these are, you can see tendons represented here. So these are all tendons that connect the muscle to the bone. And aponeuroses is another term which we use of muscles, a connective tissue that connects muscle to muscle. And so this is the epicranial aponeurosis because it connects the frontalis to the occipitalis. So this is a aponeuroses, and there's some others which we'll see in the class. Another term which we use when we're talking about muscles is our origin and insertion. I tried to use it a few minutes ago. Origin is the immovable end of a muscle, where insertion is the end that moves the limb. This has more, is easier to understand with appendicular muscles than it is with central or axial muscles. But anyway, origin in the case of the biceps would be on the scapula, and then insertion on the lower end muscles. Synergists and antagonists. Synergists are muscles that do the same action, like extension or flexion or whatever, where antagonists do the opposite activity. So the biceps brachii and the brachialis are both synergists, where the antagonists could be the flexors and extensors. For the biceps would be the triceps. So those are muscles with the opposite action. Pretty self-explanatory. So with that kind of explanation, again, there's hundreds of muscles, and all I'm going to have you learn is a group of central and pretty critical muscles. So I'm just going to focus on a few, and I think the lab has almost the same muscles that they're going to have you learn. So we'll focus on the more critical ones and not have you learn every muscle in the body. So we'll start out with the epicranium, and that I already pointed out, the aponeurosis that goes across the cranium is called the epicranial aponeurosis. And we used to call the muscle on the front of that the frontalis, and then the muscle on the back the occipitalis. But they're all really tied together, so now they call that one muscle. And so there's the bellies, the frontal belly, I love that term, of the occipital frontalis muscle and the occipital belly of the occipital frontalis. So they just pull the epicranium tight, or hold it tight, and that's represented right there. Okay, then a couple facial muscles. The orbicularis oris, very easy muscle to remember. It circles the lips, so some people call it the kissing muscle, but it just allows you to purse your lips. The orbicularis oculi, exactly the same circular muscles that surround the eye, so that allows you to close your eyes, and that's right there. The buccinator, I've got a couple muscles other than those in the face. The buccinator muscle pulls the mouth, or the edges of the mouth backwards, or when it does that, it's compressing the cheeks, if you will. Buccinator, I think, comes from something like trumpet player, at least in my mind it does. But when you're trying to reach those really high notes, that's the one that keeps your cheeks from puffing way out, Dizzy Gillespie or something. So anyway, it compresses the cheeks, and it's right here, kind of hidden underneath the large masseter. The platysma is this very large, platyhelminthes, a flat worm. So this is platy refers to flat, and it's this long, very wide, flat muscle right here across the whole neck. And so it attaches the lower jaw, it tenses the skin, but it also lowers the jaw, as we'll talk about shortly. The zygomatus major and zygomaticus major and zygomaticus minor are shown right here. The zygomaticus major is the lower of the two, and that draws the lips laterally, and you can sneer by elevating the upper lip, and that's the zygomaticus minor. The rhizoris draws the lips laterally, and that's shown right here. It's this little tiny muscle that's on top of the buccinator and some of those other muscles. got a lot of muscles of facial expression, so people will know what we're thinking, I guess. So those are some classic muscles of facial expression that we often students learn. Some major muscles that are required for chewing or mastication. The masseter, a huge muscle on the side, elevates or pulls your mandible up. So it's right here. It's connected to the mandible and up on that arch that we referred to before. The temporalis is underneath the occipitalis, and it's right here. It covers most of the side of your head, right on top of the temporal bone. And we already mentioned the platysma, but again, here it is cut away, but it pulls the mandible down, so it depresses the mandible. Muscles that move the head, one of my favorite muscles, and it's certainly a good-looking muscle, is on the side of the head. You can see it very clearly when people turn their head one way or another. It's called the sternocleidomastoid, and it lets you, or motivates you moving your head from side to side. Some muscles of the abdomen, I always think of these when I remember lab, and I used to not have TAs. I probably enjoyed you guys more because I do all the lab teaching myself and get to know you, but this week you're going to be dissecting the cat, and we had some guys that were really artists with dissection, and they dissected each of these muscle layers with unbelievable clarity. It was really cool, and you can do that if you have patience when you're in lab this week. But the outermost layer is called the external oblique, and as you see, it comes downward. It's an oblique angle. It comes downward from the posterior towards the anterior. It's called the external oblique, and it compresses the abdomen. It holds the abdomen in and depresses, pulls down on the thorax. In the center of the abdomen is a white line. They call it literally linea alba, which just means literally white line. And it's the center of the aponeurosis, the second aponeurosis that we've indicated. It's called the aponeurosis of the external oblique, and it connects the external oblique on the left side with that on the right side. So it just hooks the two external obliques together. So they're anchored here in the abdomen, so that when they contract, it pulls against that aponeurosis. If you cut away, as they've done right here, the external obliques very carefully, right underneath them, you tease between the two, you'll find an internal oblique. And what's nice is it has the absolute opposite orientation, so it goes upward where the other one goes downward. I think of it as plywood, layered plywood. So if you want to increase the strength of a very thin layer of wood, you put another thin layer with the opposite orientation. So this is a way to increase the strength of the abdominal muscles to make the next layer have the opposite orientation. There's also an aponeurosis, linear alba and aponeurosis of the internal oblique that hooks the internal oblique muscles towards that linea alba. And the rectus abdominis muscle goes the other orientation. It goes north-south, or from superior to inferior, down the center of your body, again with the same purpose, compressing the abdomen. It also, if you pull in, would flex the vertebral column, but it compresses the abdomen. So here's the third set of muscles that's trying to hold our viscera in our abdomen. And then finally, it's more of a strap-like muscle on both sides. And finally, underneath the internal oblique, there's a transversus abdominis, which goes just literally straight across the abdomen. And so it is, again, doing the same thing. So there's 4 layers of muscles all trying to compress the abdomen. You'd think that this would be sufficient, that our belts wouldn't end up kind of parallel to the ground like we do. But boy, it's evidently we've evolved all kinds of muscles, and we're trying to keep our viscera inside our abdomen. Still, a lot of us can't quite do it. But anyway, it's kind of a neat story. So in lab, if you want a challenge, see if you can tease out those 4 nice layers, and you can if you have patience and see each one of those layers. Okay, this is I think, a better diagram of those layers from another perspective. So here's the external oblique. Here, the internal oblique is over here. They pulled the external away. Here's a rectus abdominis, and the transverse abdominis would be way over here. So anyway, all the layers are there, and this is another way to look at it. If you have a cross section, you can see the rectus abdominis is the only muscle in the most anterior part of the abdomen, and those other three, external oblique, internal oblique, and transverse abdominis, form a three-layered wall around the abdomen. And that's all I was going to do today. And so the muscles that move the appendage will do those that I want to worry about on the one. So I have a couple eye-clicker questions for your entertainment. Kind of hard to write questions that are very difficult, but this is what I've come up with. Okay, the first question. Protein tethering, the protein that couples myosin to the M and Z line, what was that one called? Okay, maybe another few seconds. Looks like there's at least 140 here today. I'll go to 45, so 5 seconds left. 2, 1, stop. Okay, let's see what you got. Looks like everybody got it. Remember, titin is the largest protein we know of, and it's this huge protein that's in that sarcomere that holds the two, I don't know what that's about, that holds the thick filament in position. Okay, so that's the first question. The second question, oh, I was just showing you where titin is. So titin's right here. It's in the little blue line that's hooked between the M line and the Z line. Okay. Which domain of troponin binds to tropomyosin? Pretty easy question. Okay, I think I had 44 or 45. About 5 more seconds. 4, 3. Okay, I guess I got 143 today. Okay, wow, everybody got it. There's no such thing as troponin M and A. I don't know where I got that from, but there's 3 troponin I, C, and T, and the one that hooks to tropomyosin is T for tropomyosin. So here is the troponin T, I, and C, and here's actin, the thin filament, and here's tropomyosin. So troponin T hooks to tropomyosin. Okay, number 3, the primary class of contractile tissue in the following tissues is smooth muscle except for one. So all of these are smooth muscle except for. These are very simple questions. Okay. We'll go to 143 and then quit. I think that's everybody. 2, 1. I think that's everybody. Okay. And E is definitely right. The atria of the heart has cardiac muscle. All these other have smooth muscle. Number 4. Myosin light chains in mammalian skeletal muscle contain, which is true for myosin light chains? Okay, I'll give you a couple more seconds. All right, well, come on, one more person. Take a guess. Too bad. That's it. Okay. Had to have one like that, I guess, don't I? The light chain, remember there's 2 of them. One of them is called the regulatory, and plays some role, we're not even sure, in the regulation of myosin ATPase activity. The other seems to hold the head in conformation, so none of these are true. E is the right answer. Nobody ever uses none of the above in their answers except me. So. You were told never choose none of the above unless you're in Lyon's exam. Okay, number 4. This is the 2 chains. The light chains. The heavy chain refers to the myosin itself. The one is regulatory and the other is called alkali, and it holds the position of the head in its conformation. And the regulatory, we don't know for sure what it does. Okay, number 5. In resting muscle, myosin does not interact with actin because. Okay, about 10 seconds. 5 seconds. 4, 3, 2, 1. I think that's everybody. Okay, most of you chose C, which is true. The binding site is masked, otherwise it would hook up. And I think I have a picture of that. So the reason they can't hook up is because TNI and tropomyosin block the access to the site. So C is correct. Okay. I'll see you on Thursday.